Hello, my name is Kesai Chauhan. Today I am going to speak about a topic called Central Limit Theorem for Mixing Random Fields. Introduction to Mixing Random Fields. Mixing random fields are collections of random variables indexed by multidimensional parameters. They are used to model spectral data with dependencies across locations. Understanding their limit behavior is crucial for spectral statistics and probability theory. Overview of the Central Limit Theorem (CLT). The CLT states that the sum of a large number of independent identically distributed random variables tends towards a normal distribution. Extensions of the CLT to dependent variables require specific conditions on the dependent structure. Extensions of the CLT deployment variables require specific conditions on the dependent structure. Mixing conditions provide a framework to handle handle dependence random fields with proving CLDs. CLDs means Central Limit Theorem. Defining random fields. Defining random fields. A random field is a collection of random variables indexed by points in a multidimensional space. Typing. They generalize stochastic processes to higher dimensions. Examples include spectral temperature data, environment measurements, and image analysis. Dependence in random fields. Dependence describes the random variables at different locations influence each other. Strong dependence can prevent the application of standard CLDs. Weak dependence measured via mixing conditions mixing conditions allows for CLD like results in random fields. Mixing conditions overview. Mixing conditions quantify the decay of dependence between distant parts of a random field. They are formulated through mixing coefficients that measure the strength of dependence. Different types include alpha mixing, pi mixing, and beta mixing conditions. First, alpha mixing coefficients. The alpha mixing coefficient measures the minimum correlation between sigma algebra separated by a certain distance. It decays to zero as the separation increases, indicating weakening dependence. Fast decay of alpha mixing coefficient is often required CLD proofs. CLD for alpha mixing random fields. Under suitable decay rates of the alpha mixing coefficients, a CLD can be established for sums over the field. The theorem typically involves normalization of the sum and convergence to a normal distribution. This results extend classical CLDs. This results extend classical CLDs to dependent spectral data. Conditions for the CLD in mixing fields. The key conditions include summability of mixing coefficients and moments of the random variables. The random variable should have finite second moments for the variance to be well defined. The decay rate of the mixing coefficient influences the rate of convergence. Sketch of the proof strategy. The proof often involves blocking techniques to approximate the field with nearly independent blocks. Covariance inequalities are used to control dependence across blocks. Tightness, tightness and finite dimensional convergence are established to prove the CLT. Applications of the central limit theorem. CLTs for mixing random fields are used in spatial statistics, environmental modeling, and image analysis. They enable hypothesis testing and confidence interval construction for spatial averages. These theorems help validate statistical methods applied to spatial independent data. Spatially. Challenges in extending CLC's results. Strong dependence or slow decay of mixing coefficients can invalidate CLT conditions. High dimensional fields require restrictive conditions due to increased complexity. Ensuring finite movements and decay rates often involves technical assumptions and careful analysis. Next, recent research developments. Advances include establishing CLTs under weaker dependence conditions. These are ongoing efforts to extend results to non-stationary and non-ergodic fields. New techniques involve coupling and blocking methods tailored for complex spatial structures. Practical considerations. Verifying mixing conditions in real data can be challenging and often realizes relies on model assumptions. Simulation studies can help access the validity of CLT approximations in specific cases. Proper normalization and ensuring finite movements are critical for applying the CLT in practice. Mixing conditions provide a framework for extending the CLT to dependent random fields. To decay rate of dependence influences the applicability of the theorem. These results are vital for statistical inference in spatial and environment science. Future directions. Research is ongoing to relay assumptions and handle more complex dependent structures. There is growing interest in non-stationary and anisotropic random fields. Developing computational tools for verifying mixing conditions remains an important area. Recent research developments. Advances include establishing CLTs under weaker dependence conditions. There are ongoing efforts to extend results to non-stationary and non-ergodic fields. New techniques involve coupling and blocking methods tailored. Mm. Summary of key points. Mixing conditions provide a framework for extending the CLT to dependent random fields. The decay rate of independence influences the applicability of the theorem. These results are vital for statistical inference in spatial and environment science. Future directions. Research is ongoing to relax assumptions and handle more complex dependent structures. There is growing interest in non-stationary and anisotrophic random fields. Developing computational tools for verifying mixing conditions remains an important area. Conclusion. The CLTs for mixing random fields bridges the gap between dependent structure and normal approximation. It enables rigorous statistical analysis of spatial data with dependencies. Continued research will expand the scope and applicability of these fundamental probabilistic results.